Hi all, welcome to the seventh tutorial here in Operation System course. Today we are continuing our discussion on xv6 operation system, which is a redundant operation system. Today we're going to focus on processes and some system calls. I'm gonna describe some of the basics related to processes and system calls. And next week, we're going to delve deeper into this discussion by finishing with context switching, process creation, trap handling. This is going to be a two-part tutorials, which are really much related. So here we're going to start. So generally, when we talk about the process, this is a very important task of the operation system, since the operation system is responsible mainly to run processes, otherwise it is not doing anything. So the operation system is responsible for concurrently running multiple processes on one or more CPUs, meaning the operation system is responsible for our keyboard, along with the mouse, along with some commands that we do, like ls, cd, and so on. And also processes such as kernel processes, where we are, like, for example, adding USB to the computer, then we have interruption, then we should have another process to handle this, which is a kernel-based process. And today we're going to start our discussion related to these processes and about the system calls. And we're going to build our own system call in the xv6 operation system. We're going to see how to implement it. And also see other kind of system calls, such as we'll see right away. Okay, so such as open or wait and open the files, and we'll see later on more and more system calls. So as we said, the operation system is responsible to create, run, and terminate a process, meaning that the process has several states. We're going to see it right away. And it's going to do a context switch from one process to another, meaning saving the register, saving the state, saving memory of the heap and the stack of the process, and then moving to another process. This is the context switch. We're going to discuss it in more depth next tutorial. And the operation system is responsible to handle any events, for example, system calls. Okay. So generally, this is something that we talked last week a little bit about the BIOS. We talked about that the BIOS is a kernel based, meaning that it sits on this address. So each process address space maps the kernel instruction. This is the kernel instruction, this is the kernel, and data, as well as the user program memory. Each process has a user space and a kernel space. For example, when we first on the user space, and then we get another interrupt or anything, then we move into this space, and then moving back to the user space. So as we said, when a process invokes a system call, meaning interrupt from a USB drive or using the memory with an error, such as a division by 0 or anything like this, system call execute in the kernel, mapping of the process address space, meaning when you're moving to this kernel And this arrangement exists so that the kernel system call code can directly refer to the user memory, meaning that when we are in the kernel, we know where the user is, where it is based, right here. And as we said, xv6 address space map the kernel at high addresses starting from 801100. Okay, so this was the beginning. Next, operation system maintain all information about an active process in a process control block. Means that we have a struct where each struct in its cell we have another different process. In the xv6 this struct is called a proc, struct proc, we're going to see right now, and in Linux there is task struct. So this struct proc is a struct with each cell is a process 1, 2, 3, and in xv6 this structure has a limit of 64 processes, meaning it cannot we cannot have more than 64 processes. It's static, and for Linux it's dynamic, of course. So all the process control, this process control block are all active processes, is a critical kernel data structure, maintained as part of kernel memory, meaning wait, I have difficulties with this. Okay, meaning it sits here in the kernel. Okay, let's continue. So here we have the process structure, struct proc, which is the state of a process, per process state, and which is you can see this code in the PDF, the PDF of xv6 right here. You can search it in this line. So how this every process, what does it have? So it has a process ID, process state, which has several states, unused, intermediate state between unused and sleeping, and runnable, which wait to be run, running, it's running right now, and zombie, which is about to be killed, meaning finishing its execution. So these are the states. We have several other states like file or file, which is generally every process has 1, 2, 0, 1, and 2, which are the standard output, standard input, and standard error. And if you have another file that you're accessing in this process, then you add to this array. And you have other stuff we're going to discuss later on, such as the page table. Each process has its own page table, meaning it's mapping from the virtual memory into the physical memory. And the size of the process memory, the parent process, who call this process. Trap frame, we're going to discuss it next tutorial. Context, which save all the contents of the process, and so on, and the name, of course, and account directory, and so on. Okay. Now each process has a thread of execution, meaning by default each process has a thread executing. It executes the process instruction. Of course, when you have multi-threading, we can have multiple threads running a process, but here in xv6 we have one thread running a process by default. Thread can be suspended and later resumed. we're going to talk it right away, that the operation system, if you want to run all processes concurrently, then it have um, a certain time limit for each process to run, and then in round robin, meaning one after the other, and consecutively, meaning one after the other, and then returning back. You have each process running a certain time, and then it's suspended, meaning it's going to sleep, and we need to be, sorry, going to be runnable, and then another process running, and so on. Regarding the sleeping state of a process is enabled when you are accessing, for example, the disk, so you're waiting a long time and so on. Okay, to switch transparently in between processes, the kernel suspend the current running thread and resume another process phase. Of course, we save the state of the old process and then we move into the another process. Okay, much of the state of a thread, local variables, function call, return address is stored on the thread stack. As we've seen before, we save the registers on the stack, which also has the state of the thread. And when we go back to this thread, we're updating the instruction pointer and the stack pointer. Thereby we can reaccess the old variables of the old thread. Okay, as we said, each process has two stacks, a user stack and the kernel stack. Okay. Okay, so as we said, we have the kernel stack and the user stack. And when we move from a user space, meaning from user process to a kernel system call, then of course we save the register state, meaning there are some registers such as the general purpose registers that we saw, and it was saved in the user stack during a function call. But when we are back into this user stack, we restore this data. And likewise, the CPU context is stored also in the kernel stack, meaning there are some registers that are more of kernel based, meaning, for example, we saw CR3, which is responsible for, for the page table, and also there are segment registers it responsible for the segmentation, moving from virtual memory into a physical memory. So there are two types, as said, of kernel and the user information that we save on each of them. So why separate stack? Because the operation system doesn't trust the user stack, meaning we don't want the user to access, for example, CR3, which is this paging of process and moving from virtual memory to physical memory, because we don't want the user to be able to access the physical memory manipulation, so that two processes cannot interfere each other. And this this area is linked. This stack is we're able to get into this using the struct proc of each process. Okay, so beginning of work, when we are having a user process, then we have of course a user instructions, and the user stack as we use it is in use, and the kernel stack is by default is empty. And when a process enter the kernel, for example, using a system call or interrupt, then of course we move into the kernel stack, and the kernel code execute on the process kernel stack. So of course when we move into the kernel, User stack is still containing data, but we're not using it. And so as we said, this, and of course, process further alternate between using the stack and the kernel stack, user stack and the kernel stack. Of course, the kernel stack is separate and protected from user code so that the kernel can execute even if a process has destructed the user stack. Okay, as we said, we have another area in the proc stack, which is O file, which state all the files that we are accessing. By default, we have the first three files in this array, which is by default the standard input, standard output, and the standard arrow. And if we have another files that are opened by a process, then we enter this into this array. Okay. So also, as we said, we have another entry, which is the page table of each process. So every instruction or data in the memory of a process has an address that is accessible using this page table. So of course, the virtual addresses starting from 0, as we saw here. The virtual memory of the user stack, the user memory is starting from 0. And the actual physical address is based upon this page table. So this page table maintains a mapping between virtual address and physical address. More on this 2 weeks from now, as you see here, and tutorial number 9. Okay, in order to access the process table, struct proc, we have a lock, which means that only one process can access this structure, so that no two processes can access the same structure. So let's see an example. As we said, of course, the proc structure has a limit of 64 processes that can run due to this limitation. So this is a fixed size array. In real kernels, we have dynamic size data structure. So is, for example, the CPU scheduler that the operation system loop over all runnable processes. Pick one, set its running CPUs. For example, we acquire this lock, meaning that we are and now we want to read or do something in this structure. So we are going through all the array, and if the state of the process is not runnable, then we continue, and this finish when we have one process that is runnable, and we're going to set this process. And we'll set this process, and then we're going to change the state of the process to be running. More on this later on. This means we're going to switch it to the user virtual memory of this process. More on this later on, and we are in the state of running. Okay, this is round robin searching for a runnable process. Okay, here we're going to see a little short explanation of a process going into sleep or going to be healed, meaning that the process finished its time limitation and now it's going to be runnable state and waiting for the process to regain its running state. So for example, in the sleep, what we have is, of course, we're going to lock the p table, and then we're going to change the state into sleeping and start the scheduler that we saw in the last slide, and this more info I'm going to discuss it later on. And the yield, when we give up a CPU for one scheduling round, then of course we acquire the log, we change the state of this process to be runnable, schedule, and release the lock. Okay, so in summary, we saw some basics explanation of the PCV structure, meaning the struct proc, and the list of processes, the scheduler code, and some of the state transitions. And we did it quickly because we're going to revisit it later on in much more detail. So this was just the beginning. So now we're going to discuss in more detail how the processes a system calls is operating. So for example, the shell, how the shell is operating. So we have, first of all, when the xv6 boots up, it starts in init process. We saw it last tutorial, meaning the init, what is this? Nice. And the init process, and then this init process call, this is the parent process call, meaning using the fork to the shell. And now the shell calls user programs such as ls and so on, and then after this process is finished, it's moved back into the shell. So as we said, init forks shell, which is another user process, which we're waiting for an input. So the shell execute the user commands, the shell read the command, shell which we're going to see the implementation right away, but the shell read the command from the terminal and fork the child, new process. We're going to have another process in the p table. The child runs. When the time of the child arrive, it runs. It calls this function exec, which initialized this process. The shell, the parent, wait for the child, for example, ls to finish, and this repeat. Some commands have to be executed by parent process itself and not by child. For example, if I'm writing in the shell cd, then we're not creating another child process since we want to change the current directory of the parent, the shell directory, so we are not using another process. And some commands are directly executed by the shell itself without forking a child. Okay, so cd is an example of this. So this is the main function of the shell, waiting for an input, and then reading this input. If this input in the shell is, for example, cd, as we talked, then we execute this command inside the parent, and if not, then we're using the fork to create this child process, and then we're going to run this. This run cmd parse cmd, meaning that you're going to execute the exec function that you're going to see also later. So this function calls the user command, and then the parent wait for it to finish, and then it exit when it finish all the inputs. Okay, here you see a system calls that are available to the user program that are defined in the user library header called user.h. So you see some example of system calls that we have, for example, fork, exit, wait, pipe, read, write, kill, close, so on, open, and make the change, etc. And we're going to discuss in more detail this function, and exit function, wait function, in a few minutes. So, okay, also in addition to the system calls, we have also implementation of malloc and the str copy. Okay, and this code is not available in the PDF, in this PDF, since the PDF covers only kernel information, kernel code, and this is a user space code that we are using, so we are able to see it only using the user.h. If you want to see this, so let's see here. Using the vim function command and user. So here you see all this system call that we saw right now. Also we have the malloc that we talked, the str cmp and the str copy that we discussed right now. Okay. So when we call a system call, the system call implementation invoke a special trap instruction called int in xv6 in x86. So in the usys.s, which is an assembly code, you see the implementation here. Here, for example, you call fork, system call, exit, wait, and so on. So what it does, it's going to this implementation, going to the name, for example, fork, and execute fork by moving the system call number, sys fork, for example, into register EAX, such that the kernel will expect EAX to be the suitable number, system call number, in order to run the code. We'll see it right away how it is implemented, and then we're going to use int t syscall, which is going to provide this trap, meaning the interruption, and moving into this kernel mode. And after this, it returns into the user space. So we're going to discuss it in more detail later. Okay, so let's see some implementations. For example, let's see user.h that we just saw. Here, user.h has all the system calls. Okay, let's see now usys.s. So here you have all the calls of system calls, which call this assembly code that we just saw. Okay. So user.h contains the system call definitions. usys.s contains a list of system calls exported by the kernel and the corresponding invocation of the trap instruction, meaning the int instruction that you just saw, which hold the kernel. Let's see syscall.h. Okay, this is the numbering of each system call. So that the kernel will know according to this number which kernel function to execute, where there is a change directory function, wait, exit, and so on. Okay, so syscall.h contains a mapping from system call name to system call number. Every system call must have a number assigned here. Now let's see syscall.c, which is the implementation. Here we have the implementation of each system call. So let's see an example. System call by its number. Here you see a mapping from a number into the function. So how it's work generally, we have a system call that according to the number of the system call, it will implement the according system call. Okay. So as written, syscall.c contain helper function to parse system call arguments and pointer to the actual system call implementation. So it's point into the actual system call implementation that is implemented in this file. For example, let's say sysproc.c. So here you see the implementations of the system calls that we saw. For example, fork, then it a fork function, exit, execute the exit function, wait, and do the wait, and you have another like sleep that we saw before, which changed the state of the process to sleep, and many more. Uptime, just count clock ticks of interrupt, and okay. So sysproc.c contains the implementation of the process related system calls. Let's see defs.c. Sorry. Def.h. So you see definitions of important functions. For example, you have the calloc function, you have the write, read, and more function that we are using in the kernel and also in the user. For example, cprintf, exec, which execute a user command, and many more. So this is a definition file, scheduler, and so on. Okay, let's see proc.h. So here in proc.h you see the structure of the proc, meaning the PCB, and the states that possible in each process, and of course the context, meaning the important registers that we are using. Okay, what's more? Okay, that's it. Okay, contain the structure proc structure. Okay, let's see pros.c, which is the implementation. Okay, so here, okay, so we said proc.c contain implementation of various process-related system calls and the scheduler function. This file also contains definition of ptable. So any code that must traverse the process list in xv6 must be written here. We're going to see right away and our own system call we're going to add to the xv6. So this will be more understandable. So here it is. We're going to use our uptime system call, which is a very simple, I mean, the most simple system call implementation in xv6, which takes no any arguments and return just an integer value, which is the timing, the time of the interruption. So let's see where this system call uptime is written. And we're going to do this by using this command grep uptime and Kohavit CSH, meaning we're going to search all C code, H code, and assembly code to see all the source file, which include the word uptime. Okay, so we're going to grep uptime CHS. Those are all the all the occurrences of uptime in the xv6 implementation. We have 5 functions where it is related in the syscall.c, syscall.h, sysproc.c, user.h, and usys.s. So let's see each. Here you see the explanation. I'm going to cover it using our own. Okay, so here I'm inside the first one. This is call.c. So if I want to search, I'm using the slash, then uptime. This is the first occurrence, which initialized the header of the uptime syscall. And then we have another occurrence using the escape n, and we have another occurrence over here, which set the relation between the number that we're going to assign to the uptime and the sysuptime function. And we have no other occurrence. Okay, this is regarding syscall.c. Now let's see syscall.h, which define define uptime to be a number of 14, which is important for the kernel to run, meaning that we saw that before moving into the system call, we assign to register AX, EAX this value so that the kernel will know which system call to run. So this is the definition. Okay. Next we have syspros.c. Let's search. Okay, this is the implementation of uptime. You see it right here. Okay, and let's see user.h, which have this header of uptime. And lastly, we have the assembly code that we add here that call the int function, the interrupt, in order to run in kernel the system call, and that's it. Okay, so all we said is written here. Let's move into implementing our own system call. So this is already implemented, and the code is uploaded into the model, but let's see how we do it. So I want to add a system call that is called get counter. It is similar to the uptime that we just saw, that it doesn't accept any parameter. So every process will have a counter to be initialized to 5, and each call to the get counter system call will increase this value by 1, and the system call will return the get counter value. And we're going to use hello world.c, that is a user command that we added to the xv6 operation system. And using this function, we're going to address the new get counter system call, which is unrestrictable to hello world. We can also add this get counter system call to another user space command, such as wait, cd, and so on, which are another user commands. So let's see how this system call is implemented. So as I said, I already included this get counter in the code. So let's see where did we implemented it. So actually, we need to add this this get counter in approximately the same places as uptime. So let's see get counter when we added this. So first of all, we added, okay, let's say it last. We added, let's see, which one? The last one, syscall. We added this syscall, which enable us to run this interrupt to move into the system call implementation to the kernel. And then we have the user.h, which set the header for the get counter. Let's move this real quick. Next you have syspros.c, which here we add this implementation. This is the core base of the system call, which return we added to mypros, which is the structure of the process. Let me show you. We add to syscall to pros.h. If you see here, the per process state, we added this get counter. This is for each process we have this values. So we added this get counter, which is initialized to 5, and then each time we call the system call, we add this by 1. So let's see it. For example, proceed.c. You see here that we initialized the value of let's search get counter. So you see when we allocate the process, this is the initialization of the process. Then here, when we found this process, meaning that we right after we update the PID, then we set the get counter to 5. This is the initialization. Okay. And after initialization, of course, we add the definition. We add another number to this system calls. Okay, you see we added this system call to the general system calls. And if, for example, we are saying this, and we have implementation of getCounter, which update on the structure of the process, the getCounter to be +1. And lastly, we have the hello world.c, which we're going to call this system call, which we have a 4 of 10 values that we going to call this get counter, and we get the counter value, and then we print it to the shell. So let's see how it is. So of course we make we write make. So we already made it. Now we're writing make qemu nox, and then if I write, for example, hello world, sorry, then you see the implementation of the system call, which initialization is 5, and then we're calling it 10 times. Also important that if we rerun this hello world, then this value is still get to 5 and then increased, since every time we call into hello world, this process enter, and then it finished and killed, and then when you run hello world again, then it initialized once again, and therefore this value is initialized to 5 every time. Okay, also another important issue is, let's see, the make file that a little bit changed since we added this hello world user command. So if I'm searching hello world, so we added to this user commands in the extra, and another place is here in the user programs. So these are the two places in the makefile that we need to add this hello world in order to compile this hello world with the actual xv6 implementation. Okay. So this is what we have made. This is what we done. So we add the system call to the proc.c, proc.h.proc.c, and so on. Okay, there are other system calls implementations that are a little bit more harder than the uptime system call that open wait for an argument of string and integers. It's going to open a file, so it's need a string and an integer. So the implementation is used. The implementation is in syscall.h, syscall.c, and use sys.s, similar to what we saw in uptime. However, since this open system call wait for um, for arguments, then we are using those functions argint, argptr, argstr, and arg file descriptor that are going to be used in order to read the arguments. Those functions are calling a lower level a function called fetchInt and fetchStr. We're going to discuss it a little bit more next week, so I'm not going to show more information about it. And of course, the implementation is in xv6. You can see it yourself. For example, sys open, which is the main implementation of this system call, implemented in the sys file.c in those lines. And so we're going to discuss a little bit more about other system calls in the next tutorial. Okay, so that's it for now. Thank you very much, and see you next week.